Welcome to section 3.2. Today we're going to talk about properties of determinants, but let's start off with a review of computation using cofactor expansion. So for this first determinant, I'm going to do cofactor expansion and I'm going to do it across row 1. I could do row 1 or column 3 in terms of the easiest computation because I want to pick a row or column with as many zeros as possible. So this is going to be 1 times -1 to the 1 plus 1, which is 2, and then I want the subdeterminant for -1 to -1. I cross out first row, first column, plus 5 times -1 cubed, and then I want the subdeterminant, cross out first row, second column, 2 to -1, and then I want 0, and I'm not even going to write down the rest of it because I'm going to multiply by 0 anyway. So when I do the computation, this gives me -2 plus 5 times 0 is 0, which is -2. Okay, next one, it's a 3 by 3. However, computation is very easy because this is a triangular matrix, so the determinant is just the product of the diagonal entries. 3 times 1 times 4, which is 12. Okay, which statements make sense? First one, find this matrix 1, 2, 2, 1. This reminds me of that joke, find X, where students ask to find X and they just circle it and say, here it is. So this one makes no sense. The matrix is staring us in the face. The next one, find this determinant. Yeah, that makes sense. Third one on the top row, that makes no sense because you can't find the determinant of a non-square matrix. Moving on to the next row, find the determinant of the matrix 1, 2, 2, 1. That makes good sense. Just a different notation. These mean the same thing. Okay, the next one on the second row is just an embarrassment to math. That makes absolutely no sense. It's just 4 numbers hanging out there in space. The next one, you could read it 2 ways. Find the determinant of the determinant, in which case it would make no sense. But if you read those bars on the outside as absolute value, that does make sense. So if we read that, which we would have to make sense, this is absolute value, find the absolute value of the determinant. That makes sense. Okay, the next one on the last row, we're saying one matrix is row equivalent to another. Okay, that makes good sense. But compare that with the next one on this last row. We're saying one number is equivalent or row equivalent to another. That makes no sense. So what I want to point out by the examples on this last row is that when you're talking about determinants are either equal or they're not. So you don't want a row equivalent here. This would have to be an equal to make sense. Okay, so this next set of results we were working towards last time, and we saw they're true for elementary matrices, but we're going to see now that they generalize. So in English, the first result tells us that when we're finding determinants, the way I like to think of it is that we can pull a scalar out of a row when we're finding a determinant. And I have an example there so you can see what I mean. Okay, the next one, when I swap rows and I'm finding determinants, that's going to change the determinant by a minus sign. So swapping rows changes determinant by a minus sign. And the last one tells us that row replacement has no effect on the determinant. So property C is really a great one. So let's see how we can use these results to find determinants. So in this first example, I've got a 3 by 3. If I were just to find the determinant the way it is, I would have to do cofactor expansion and I would have to compute 3 subdeterminants to do that. And it would be quite a bit of arithmetic. Wouldn't be too hard, but it would take a while. So what I've done instead is that I've decided to do some row replacements to get myself several zeros in the first column. So I've written down the row replacements I did. And again, you want an equal between these two determinants. You don't want a row equivalent sign. Okay, at this point right here, I can do one of 2 things. I can do cofactor expansion down the first column, or I could keep going and try and get this into echelon form. I'm going to do the former rather than the latter because I don't want to introduce fractions. So now what I'm going to do is cofactor expansion down this first column. This is going to give me 1 times -1 squared. And then I've got subdeterminant -6, -5, -8, -7. Now a 2 by 2 determinant is very easy to compute. So this just gives me 42 minus 40, which is 2. All right, the next example I chose because I'm going to do one of each of the properties to illustrate how it works. I'm going to start with cofactor expansion on the second row. So this is 5 times -1 to the 4th power, and then subdeterminant, I'm going to cross out second row, second column, 2, 6, 10, 1, 3, 4, 2, 7, 11. Now I'm going to pull a 2 out of row 1. So I've got 5 times 2, which is 10, and 1, 3, 5, 1, 3, 4, 2, 7, 11. Now I'm going to do 2 row replacement operations. I'm going to use this one to kill off the 1 and the 2 below. So I'm going to do 2 row replacements at once, and row replacement does not change the determinant. So this is 10, leave the first row alone. Second row becomes 0, 0, -1, and the third row becomes 0, 1, 1. Now I'm going to do a row swap between rows 2 and 3 so that I have a triangular matrix. So that's going to change the determinant by a minus sign. Okay, now I've got a triangular matrix, so I can just multiply the diagonal entries, and I get -10 times -1, which is 10. Okay, this next one is going to really force us to use properties of determinants. I'm given that the determinant of this 3 by 3 matrix is 7, and I want to find the determinant that's given there. So what I want to do is work my way back to the original matrix and keep track of any changes I make to the determinant. So the first thing I'm going to do is I'm going to swap rows 1 and 3 so that I have the ABC on the top. And when I do that, that's going to change my determinant by a minus. So now I've got A, B, C. Second row stays the same, and the third row is GHI. Okay, now the order is important here. The next thing I have to do is replace row 2 with negative row 1 plus row 2 to get rid of this A, this B, and this C. I can't divide or I can't pull a 2 out of row 2 because there's no 2 in front of the ABC. So I'm going to do a row replacement operation that isn't going to change the determinant. A, B, C, and second row is now 2D, 2E, 2F. Third row is G, H, I. Now I can pull a 2 out of row 2, and that will change the determinant by a factor of 2. So now I've got -2, A, B, C, D, E, F, G, H, I. Great. That's the determinant I was given. This is -2 times 7, so I get -14. All right, some more properties of determinants, and I've combined a bunch of results in your textbook into just one big blob here. Theorem 4, which is number 1 here, just generalizes a result that we already have for 2 by 2 matrices. A is invertible if and only if the determinant of A is not 0, so we can add that to the bottom of our IMT. Number 2, which is theorem 5, tells us that the determinant of A transpose is the determinant of A. Now, this should not be a surprise because cofactor expansion works across any row or down any column. But the columns of A are the rows of A transpose. Okay, number 3 tells us the determinant of a product is the product of the determinants. Number 4, we're going to prove in a second. And number 5, we saw in the last class, if we scale a whole matrix A by a scalar K, then that will change the determinant by K to the N, where N is the size of A. All right, here's a proof of theorem 7. Since A is invertible, its inverse exists, and A inverse A is the identity. This implies that the determinant of A inverse A is the determinant of the identity. Just take the determinant of both sides of that equation. Now, this implies, by number 3, that the determinant of A inverse times the determinant of A is 1, because the determinant of the identity is 1. All right, now moving over here, this implies divide both sides by the determinant of A. The determinant of A inverse is equal to 1 over the determinant of A, which is what we were trying to show. Now, this makes sense because the determinant of A is not 0 by number 1, because remember, we're assuming A is invertible to begin with. All right, let's use these properties. We've got two matrices, A and B, and we're told the determinant of A and we're told the determinant of B. Let's find the determinants stated here. Determinant of AB, so this is the determinant of A times the determinant of B, which is -1 times 2, so -2. Okay, B, this is equal to the determinant of B times B times B times B times B, but determinants distribute over multiplication, so this is just the determinant of B times itself 5 times. So this is the determinant of B to the 5th power. 2 to the 5th is 32. Okay, next one. It's necessary to know the size of A in order to do this. This is equal to 2 to the 4th power, because A is a 4 by 4 matrix, times the determinant of A, which is 16 times -1, which is -16. All right, letter D, the determinant of B inverse is 1 over the determinant of B, which is 1/2. Okay, E, that's determinant of A transpose times the determinant of A, but the determinant of A is equal to the determinant of A transpose. So this is the determinant of A squared, which is +1. And finally, matrix multiplication does not commute. So I can't move these A's and B's around to cancel the B inverse with the B. However, if I first write this as determinant of B inverse, determinant of A, determinant of B, then I can move things around because these are now numbers. So determinant of B inverse, remember that's 1 over the determinant of B. And then I've got determinant of A, determinant of B, and these do cancel because they're numbers, and so that's just equal to the determinant of A, which was -1. All right, and that is the end of this section.